imports, we need to have our own mechanism to have self-sustained energy requirement fulfilled internally in-house in India. And that's how the critical mineral recovery project is started by the Indian government, and we pursued at our end researchers, since we have to look further in the future what will the demands of the society in the future. So in considering that, we have started the mineral recovery earlier, like we started this project 5 years ago, and then we started getting the results on it recently, like 2 years back, and we could publish it with the good values. So I will be explaining the background and foreground, like a future of these projects, and how it affects the society. So going further, as we know, since the energy derived from the crude oil or fossil fuel sources is governed by the energy output. Although we are dependent on the energy import, but the energy is governed by the US and Middle East, since we are dependent upon the imports, and the price volatility is a major concern. So our internal inflation is also dependent upon the price
Right
set
now.
by the foreign players. Hope my voice is clear to you. I hope you are getting my voice.
Yes, sir.
Yes, sir.
Fine, fine. So since we are heavily reliant on the fossil fuel imports, and hence we are our internal inflation rates are going to fluctuate as compared to the energy imports. So fossil fuel, the now Europe is European Union being smart, they are reducing their dependence on the fossil fuel imports, as well as they are moving to the more greener options, and thus they are reducing the carbon footprint also, because the carbon footprint is causing the global greenhouse effect, and hence the global warming and melting of the ice caps, as well as the rising the sea temperatures. Once the sea temperature rises, the CO2 stored in the sea, like we have um, mechanism to store the CO2 also in the sea, it also evaporates. Overall CO2 amount in the atmosphere goes up, and global warming thus is accelerated. It is not only increasing, but it is accelerated. So what we need to do? We need to decrease the carbon footprint. And now the carbon tariff is going to come. You might be aware of the industries are getting now carbon graded. Carbon graded means what is the emission of carbon of the given industry. And upon this, its electricity provision and its taxation will depend. That has already been implemented in Europe, partly in USA and Japan. So, but it is going to be a global phenomenon. But we also know the development is directly proportional to the energy consumption. So, bigger the economy, bigger the energy need, and hence the your development index is higher, or economy is bigger. It can be shown from seen from this chart. Like you can see, United States and China. So, United States has the biggest greenhouse like CO2 emission, and we know it is the biggest now second biggest economy in the world, and the manufacturing hub of the world. So it is directly proportional. What you consume is what you produce. Similarly, the United States at the second, that is the production of CO2 by the United States, global share is nearly 21%, and third share is the India. So we know we are now fourth larger economy, and our share is third. So it is very obvious for the bigger economies which are accelerating, they are going to have a bigger energy consumption due to transport, industry, manufacturing. All. Hello.
Yes, sir.
Yeah. Can I carry on?
Yes, sir.
Okay. With respect to all the economic activity, the energy consumption rate stays high, and hence the greenhouse gas production, that is C emission, carbon emission, will also stay high. So this all is going to affect the UN SDG goals, Sustainable Development Goals, and upon that our tariffs will be also in the future decided. So if we look at the overall globe, so the megatons of CO2 produced. Okay, these are the different data quoted from different agencies, and why the data are differently quoted. We have to consider the global data quoting. Why it is so? Because every agency will try to advocate their own economist voice. So if the data quoted by USA will try to push their own agenda to saying that we have the less CO2 emission, and where the data quoted by the China will have their own agenda saying that we are the less CO2 emission. So we have to compare the data globally. So if you go by the most standard data, that the Union of Concerned Scientists, that the global carbon project data, you can see China at the top, 32%, United States second, like 12.6% of global share emission, India at the third, like 6.99, and then Russia, Japan. Since we know the Japan is the fifth larger economy now, so that's how, so we are the top five players, which normally causes the 60% of global emission of carbon, and then hence we are the responsible for greenhouse effect as well. So And that is a major challenge of using the fossil fuel, because we cannot avoid the fossil fuel completely, but and hence we cannot get rid of carbon emissions. So how to tackle it? So we need to find an alternative energy source, and now world is moving toward the renewable energy and all, but there are certain issues with the renewable energy that we will deal upon. Now once we emit the CO2 and global warming goes up, then what we need to look into the CO2 separation, again the fixation of CO2. That is one of the criteria now again implemented in the industrial zone, where you need to handle your emitted carbons at the localized way. Like industries need to have their own mechanism to absorb or adsorb the CO2 and make the their that is output of industry more greener. So, but since the CO2 production is a energy derived, so the CO2 adsorption is also energy intensive. Means it requires a high amount of energy. You can see the BTU of 7210 for 400 megawatt of energy. That is, it has an energy penalty of 22%. That is to reduction in the CO2. If we capture the 270 tons of CO2 per hour. So what is happening? So basically, CO2 production and CO2 capture, it's both are going to be tragedy. And if the UN SDG goals are implemented, and since they are in the procedure now, so industry is going to adapt. So so every industry crossing that limit will be going to have an energy penalty, high tariffs in their electricity bills, or higher unit charges, as well as the limitations in their production. So the carbon technology, adsorption technology needs to be implemented in a more efficient manner, so that the adsorbents will capture the more, or will capture the more amount of CO2 in a less volume, or in a less or in a less cost intensive adsorbent. So there are several carbon capture technology groups available now. Depending upon the product, there are absorption, adsorption, membranes, biological and other. So biological and other are not that efficient because they are time consuming, as well as they are algae, microalgae, and cyanobacteria dependent, and others are the mineralization, cold separation. They are also not that efficient. The most efficient ways are the like absorption and adsorption. So absorption can be done in chemicals like amines, carbonates, ammonia, hydroxide, limestones. That's fine that the permanent precipitation. And adsorption is one of the best way, which can be done by the metal organic frameworks and zeolite. That is now grooming film and membranes. That is fibrous and microporous. So where the MOFs comes into play. But what could, if we are going to tackle the CO2 emission problem as well as the crude oil problem, we need to go toward the most promising energy source, and it can be renewable energy or it can be the uranium. And so I want to tell you, the uranium is still a backbone of the majority of energy production globally, still a backbone, and it is the most green source of energy production. So green, why green? So many of you will argue that it is a radioactive, so how it can be green? So green in the sense it does not have the carbon emission, or it has the least carbon footprint. So as we see, so since the energy, the projected energy demand from 2021 to 2050, so like next 3 decades is like this. So we are going to see whatever the energy demand we are having currently in 2021 is going to rise by 15%, like 15% uh, of current to the 2015. That will be like 660 quadrillion BTU. What is 1 BTU? 1 BTU is equal to 1055 joules of energy. So where this majority of energy is being consumed. So majority of energy, as you can see on the um, as you can see on the screen, majority of consumption is electricity generation. That is, and then it comes the industrial. Like electricity generation itself takes a majority amount of fuel, and then it comes to the industry, residential and commercial, light duty transportation, and commercial transportation. That is heavy duty transportation. So in that case also number of operable, so this energy generated by nuclear power systems, so there are number of operable reactors worldwide now. So you know the Ukraine-Russia war triggered the nuclear powered operations, because the Poland and many European countries closed their nuclear power reactors or nuclear reactors previous to 2020, because they were more shifting to the greener alternative, renewable energy alternative like solar energy and all. Since that instability, global instability came into the picture, and oil prices rose, so they understood the price will be fluctuate, and energy demand will be more costlier to meet. So they has to go to more reliable source, that is the nuclear energy. And now currently United States has the 93 nuclear power currently active. France has 56, which is a very high number. China has 55, Russia 37, and India 22 nuclear reactors or nuclear stations currently running. So So we are heavily dependent upon the nuclear energy as well. So we are dependent upon the yellow cake. What is yellow cake? It is a uranium oxide cake. That is a fuel for the nuclear reactor. But from where this yellow cake is coming? The yellow cake is coming from the primarily from the land mines. So like land mining. So but there is an issue with the land mining because land mines are depleting now. The uranium mines are getting reduced day by day, and since we will be going to face the crisis of land uranium as well. But what is the other option? The other option is the water body, that is seawater. And I would like to tell you that although in seawater the uranium is in low concentration because the water of seawater volume is very big, highest volume on the earth, but the amount of uranium in the seawater is 1,000 times more as compared to the uranium in the land mines. So, as we know, the pertinent energy crisis is affected by the declining fossil fuel reserves, energy transitions, renewable energy variability, geopolitical tension also the reason for the energy crisis, their price volatility, carbon reduction goals is imposing reduction in the import of fuels like crude oil, and energy security concern also is the main reason which can make us go for the alternative energy option. So thus it necessitates to the us to the look at for the uranium as a one of the backbone for the energy generation, and thus we need to look for the uranium extraction because the uranium extraction more the efficient uranium extraction, more the efficient will be the or less costlier will be the uranium derived energy availability. So what we need to do? We need to have the most efficient mining at the bulk level. And why uranium extraction will help us? Because it ensures the energy security. Because in renewable energy sources like solar and wind, there is energy output, but it is not in a bulk and it is not a steady. And for most of our industries and internal operations, we need a steady output, steady base load. So nuclear energy is one of the forms which gives us a steady and reliable base load. It gives us the energy security, long-term fuel supply. That is, the uranium has a bigger half-life span, as well as the for technological advancement and nuclear power generation. Uranium thus becomes a core of it. So what uranium extraction the standards? What says they are the uranium extraction is going to be the one of the seven major challenge in the globally. There are seven separation processes which actually governs the world. Where ammonia production is one of them, and uranium production is also one of them. So IAEA is an international atomic agency. It says the sole source of energy efficient technology will remain uranium in the future, and thus we need to look forward the uranium as a major source. And so far we know the uranium is 1,000 times more in the seawater as compared to the land mines. So, but the now removing such a uranium from a seawater is a big challenge because in seawater is a bulk and for concentration of the uranium is a 3.3 parts per billion. Means it's ultra trace. This is called ultra trace concentration, ultra low concentration. So how do we do a recovery of this uranium? So there can be metallurgy like acid alkaline leaching, but it won't work out in the seawater case because the volume of seawater is so high, so we won't be able to process it to the metallurgy. So then now the extraction method. What is the extraction method? We need to have the adsorbents or adsorption assembly or adsorption beds which can take out the seawater uranium, which will selectively take out the seawater uranium from the seawater and remove all other cations, and thus this uranium can be concentrated. And there where the porous material comes into the picture. So MOF is one of the porous materials. So since then how we can derive this from the MOF? So before going to the MOF, we need to look into the porous material. What are the porous materials? Porous materials are not only solids, but they are the liquid. The simplest form of porous liquid that we all have is the blood. The blood is one of the porous liquid which carries the oxygen inside the body and depours the CO2 outside of the body. This is the form of porous liquid. So this is the porous material. Similarly, there are porous solids like we know silica and all. So porous materials are generally those who contain the potential voids or channels or cavity, and that can be filled with the incoming gas. There can be gas, liquid, and or the entity which can be kept within the encapsulated within the porous surface. So the porous material must have the surface area, transfer property, adsorption capacity, as well as sometimes the catalytic activity. So what kind of porous, how these porous materials are classified basically depending upon the properties. So they are basically classified microporous, mesoporous, and macroporous. So what is microporous? The porous material which has the cavity or pore sizes below 22 nanometers, then something above 22 nanometer is mesoporous, and something above 500 angstroms and all these are the macroporous. So depending upon the pore sizes. So, but it is also divided by their adsorption capacity and separation applications. These are some adsorption isotherms, that is porous material shape. So most reliable is this, the microporous is this one, the type 1, and the mesoporous is type 4. You can see, I'm just giving the brief example that is the properties of porous material. So going ahead, prior touching the MOFs, we know that there are many porous material existing in nature. So we have a conventional, easy to classify, the conventional materials, sponges, cements, tissues, zeolites, and ceramics. So zeolites are well commercialized now. Sponges, cement is also very commercialized, but it is used for certain other purposes, construction purposes. Sponges and all, they don't have the uniform pore size. So their issue is we cannot get the uniform separations. Zeolites has the very good uniform size, but they are not tunable to that extent. And ceramics are utilizable to certain extent. And hence, world moved towards the advanced porous materials. That is the which can be tuned, which can be chemically synthesized. Their pore size, channel size, and stability can be tuned. These are the advanced porous material. Which are then? These are the metal organic frameworks, metal organic gels, covalent organic frameworks, porous organic frameworks, and metal organic polyhedras. So most famous domain in this is the metal organic framework because of their availability of library, this material formation as well as their application range. So in this only a greener material I can call it the COP because COP do not use the metal atom. Rest all and COP do not use the metal atom because they are totally made of carbon and nitrogen and all those. But remaining all three metal organic polymers, metal organic polyhedras, metal organic frameworks, and metal organic gels, they use the metal as an inherent component. Going further, how these metal organic frameworks are classified basically before to use. So there are first, second, and third generation of metal organic frameworks or the framework structures, which are the first generation is which are the stable only in presence of guest, like it is shown. Once the guest is removed, their three-dimensional porous crystalline structure will collapse. Second is the guest can be removed and added. The second is the more stable structure, second generation structure, where the guest can be taken out, structure still stays stable, and guest again can be encapsulated. But the third generation is a more attractive. Third generation, the structure is dynamic and guest triggered. So it means when the guest is inside and outside, they can undergo the transformation, which is inherently in dynamic nature. There can be the layer shift, there can be a change in the pore size, and hence since the pore window changes, so the property of the pore also changes, and the incoming and outgoing gas, the selectivity also changes, and they have the very good interplay. So there can be the 1D, 2D, 2D integrated, 3D pillar, 3D expanding shrinking grids, or 3D interplanetary. These are definitely the identified types of the structures. And here it has been on the left side of the slide, the ionic MOFs has been shown. Why ionic MOF? Because it is necessary to it is very necessary to have an ionic MOF to have the ion exchange. Since the uranium is a cation, since the uranium is a cation, to remove the uranium, we need to have anionic line flask or anionic assembly. And this anionic assembly is nothing but the anionic MOF. And generating such an ionic MOF is another challenge. So we will see the how to generate these MOFs. What are MOFs exactly? MOFs are the long order crystalline porous frameworks which are made up of metal nodes and organic linkers which form the three-dimensional, two-dimensional, or even one-dimensional change. But they should essentially have the porosity. The porosity is the prime criteria, and the orderness, that is crystallinity, is the prime criteria. So since we are looking forward to uranium capture, so we need to have the ionic MOF. And how these ionic MOFs can be generated basically? These ionic MOFs can be generated by pre-synthetic method, means before synthesis of MOF, we can plan an ionic metal, that is ionic metal part and the neutral ligand. It will generate the ionic MOF. Second is a pre-synthetic operation in terms of a ligand. So we can functionalize the ligand here as it is shown here. Either ligand can be functionalized or metal ion can be have in the ionic nature. Second is a post-synthetic approach. Suppose we have some MOF which has some definite core feature and which can be utilized for certain applications, say uranium capture. So what we need to do, already the MOF exists, we can synthesize. That is called as the functionalization, which is done after the synthesis, like once the MOF crystal is ready. So this is called as a functionalized post-synthetic approach. And there is a post-synthetic approach for the ligand and its functional group also. So it is also called as, suppose you don't want to functionalize the ligand, that is a linker molecule, then you can have the anion stripping so that you can change the high density anions on the metal atom. So the overall charge balance can be disturbed and hence we get the resultant charges. So there can be covalent modification or anion stripping for the post-synthetic approach. So going further, so since we wanted to extract the uranium, we need to have a kind of MOF which is stable, which is reusable, and which has the geometry which is pore selective, means it should be very selective for the uranium. Why it is so? Because seawater, since we are going to extract the uranium from the seawater, and seawater already has 22 plus cations, which can compete with the uranium extraction. So we need to be very careful about selection of MOF and its linker, because linker can be functionalized, and MOF, resultant MOF is going to have the geometry, topology, as well as the pore channels or pore voids in a such a way, and the coordination geometry in a such a way where we need to exactly recover the uranium, not other ion. There will be some competition. There will be some certain amount of other cations will come, but uranium should supersede. That is basically the prime goal. So in that order, we decided a linker, novel linker synthesis strategy. This is in-house synthesized linker. We are reporting this for the first time. This pyrogenic linker, you can see there are two nitrogens and carboxylic moieties. This linker is particularly two-step derived from the reactant like aminopyrazine and cyanofluoride in a two-step, and then cyanide intermediate is formed, which is further hydrolyzed to get acid product, which is pyrogenic acid, and this is then treated with a nickel nitrate. So to get this MOF, we have to do several trial and error, and we finally got these crystals, which are in and the 3D packing unit of the crystals is shown here, which is having the geometry and the DMA cations inside. So why it is having DMA cations inside? The reason being the crystal is anionic. Crystal overall is anionic, and dimethyl ammonium is a cation. So one like asymmetric unit generally has the nearly two DMA cations. It means the twice the positive charge is written within replaceable positive charge is replaced within the this crystalline flask per unit cell. So that is the beauty of this flask. And another thing, we have synthesized this in solvothermal method in acidic medium. So the formation of this MOF is in an acidic medium. So it is acid stable inherently. That is one of the ideal working. So these are some structural feature of the MOF asymmetry unit, and this is the metal SBU. You can see here the nickel and the triaxo bridges, giving it a very strong secondary building. This is called a secondary building unit. That is the metal and oxo groups. And you can here see the different axial view of how DMA cations are located in the pore channel, as well as these are the blue color are the nitrogens. How it is a nitrogen enriched. Why we are saying nitrogen enriched? Because nitrogen gives the Lewis basicity in the structure. If the nitrogen lone pair is exposed, then it can interact with the Lewis acidic moieties coming inside the pore channel, and they can bind them either by weak interaction or strong interaction. So these are the exchangeable basically this is an exchangeable flask having the very secondary interaction sites as well as replaceable cations in the flask. So these are the basic features of the MOFs. Going further, since the MOF is synthesized, we know the structural parameters. Before going for the application, we know we are going to do our application in water, and that water can be acidic or alkaline, slightly alkaline basically, as well as it has a different level of cations. It will be going through different temperature zones. So we need to have our MOF tested for the temperature as well as chemical stability as well as pH stability. So since the after doing the basic crystallography of the MOF, what we did, the desolvated, that is activated phase of the MOF, were treated in different acidic and alkaline medium. What we saw, we need to have a MOP at least stable till pH 5, pH 7 plus, slightly to have the real-time application in the seawater. So what we did, we exposed this MOP to the several harsh conditions like from pH 1 for 3 days to the pH 9, which is highly alkaline, like from highly acidic to highly alkaline, as well as we did a steam exposure like hot vapor exposure for 30 days as well as a vapor exposure for 30 days, and then we realize the MOF is stable down to pH 1. It degrades below pH 1, but in real time we are not going to have the pH 1. It will be close to the neutral pH. So we analyze that the MOF is quite stable in different pH ranges as well as it is the temperature stable. That can be seen here from the TGA. You can be seen the TGA of activated phase is stable up to 400 degrees centigrade. It means MOF is quite thermally stable. And then this TGA, but if it is a thermally stable, suppose we have taken a bulk of MOF crystal, and suppose it has 1,000 crystals, up to 1,000 crystal, if 800 crystal also gives the stability, TGA profile will be flat. Then how to again identify it? We should go for the PXRD. So we did the temperature dependent PXRD, where the temperature will go up and we'll see what is the change in the crystallinity. So here we have done the temperature dependent PXRD, and you can see the structure is written. So we from the 30 degree, that is room temperature nearly, we went up to 50, 100, 200, 300, 350, 400 degree in a controlled atmosphere, and we again get back to the 30 degree. So what we observe, the crystallinity is maintained as it is, so that the given MOF is 400, it is at least stable up to the 400 degrees centigrade. But how we decided the range? It is from the TGA, and then there are the microscopic imaging like FTSM. So that was the stability, but since we know it has a capacity to exchange the uranium, let's do it with the in terms of first let us do in the aquatic atmosphere, in the acidic aquatic atmosphere. What we did, whether there is a MOF leaching first, we try to understand. Okay, the physical methods we have done. Let's go for the chemical method. So we put the suppose MOF in the 100% amount, suppose say 10 milligram in a pH 1, and then we recovered after a certain time, let's say 3 days. We recovered the MOF and we measured the amount. It was like 94.3%. Means the MOF leaching in the liquid, like acidic medium, is not to that great. Means MOS stability is quite a great and leaching is lesser extent. We have done this for the pH 3, pH 5, pH 7, pH 9, and finally we understood the leaching percent is negligible, and the MOS stability is considerably high, and it is quite high at the pH 7, pH 5, even at the pH 3 also. And this is what our working range is. So before going further, what we did, we did the visual observation that we had the uranium solution, and in this uranium solution we put the MOF and we saw the immediate color change. That is, this is the MOF crystal as a pristine, means without any uranium, and this is the crystal which was dipped in uranium taken out. It quickly absorbs, in rather sense, I will say absorbs uranium. And this is the visual observation that dipped in uranium nitrate, it can completely change to yellow. And uranium cake is yellow, as I have shown in previous slide. Uranium cake is yellow color. This yellow color is due to the selective absorption of uranium. Now, what we need to see whether the uranium, after if we treat in a water or any other solvents, we need to retain the uranium in the MOF so that it can be extracted in later state. That we are going to analyze. So after doing the same and index of the MOF in the uranium crystal, what we saw, so we need to how the uranium, we not only found the uranium is on the surface, but we also found that uranium is within the crack. So what we did, such a dried crystal which are uranium exchange, we broke the crystal, we went to the core of the crystal and we did the same index, whether to identify whether uranium was on the surface only or it is deeply diffused within the crystal or interacting. So we found that the crystal, after breaking the crystal, we found that the uranium is within the crystal as well, diffused in well side. And such a loaded crystal also is subjected for the different characterization like uranium dip PXRD, then FTIR, what are the changes in FTIR, then adsorption. So we saw particularly once the desolvated MOF has a very high amount of N2 adsorption, that is 430 ml per gram. Once it is adsorbed for the uranium, like once we did a steam exposure, it goes down again, we regenerated. So means the water, after removal of water, its pore size should be or cavity should be empty. We just did so there is no greater loss in the cavity structure or the overall surface area. That was once that is assured, then we went for the capture study. What is a capture study? Capture study is nothing but the once we do the ion exchange or adsorption in a particular confined geometry, we need to do it in a certain model which will can be validated by Langmuir, Friendly, or other isotherms, so that it can be fitted into that and we can have the mathematics of it, known that what is the kinetics, what is the adsorption capacity and all. So we so before going to the seawater, we started with the modern water. What is the modern water system? It is a pilot scale where we know that we give the deliberate concentration of uranium, which is pre-calculated, and then we standardize the adsorption capacity of our own MOF, that how it adsorbs. So when we did the uranium spike deionized water, means deionized water, there is no other ion. In such a deionized water, we are spiking uranium, so the controlled concentration of uranium. So we know there is only uranium ion in this water, and now we are going to adsorb this uranium ion, the activated MOF, and we are going to know what is this fundamental behavior in the non-polluted sample or non-competitive sample. So we found that in such a case, adsorption capacity was quite high, and it was up to 1336.8, and that is milligram per gram. It is very high, means 1 gram of MOF adsorb nearly 1336.8 milligrams. That is quite high. And the overall concentration when we did the kinetics of it, removal efficiency was nearly 100%. In 120 minutes, we were able to remove all the uranium in the given stock solution. The stock solution is of 20 parts per million. Okay. So our removal efficiency was nearly 99.3% in 2 hours. That is 120 minutes. That is quite fast. Why this kinetics matter that time? Because in order to reuse the adsorbent, that is MOF, for the uranium extraction, we need to have a lowest time. If it has a time in days, then the reusability of adsorbent will goes down, then we won't be able to have the higher amount of uranium extracted in a smaller time, as well as the higher the exposure, MOF stability also goes down. So when we saw for the capture fed in DI water, so our MOF stands second in the literature. So then we went for the Langmuir isotherm. We fitted the Langmuir data as well as and French isotherm. So we can find the its order of adsorption. It is like second order. Basically, it is of second order. Then we went for the adsorption capacity for different cycles. Since we know the on the first cycle what is happening, then what we did, we have adsorbed the uranium. We removed the uranium to the alkaline KOH, like it is an ion exchanger. And then we again tried the adsorbent and placed in the water. So first cycle, second cycle, third cycle, fourth cycle. So you can see the first cycle adsorption capacity was 1330, 1336. In second cycle 1304, third cycle 1267, and fourth cycle 1273 milligram per gram. So there is a decrease, but it is a marginal. If we consider this decrease over the cycles in the percentage, we can see the first cycle considering 100% of adsorption capacity. Second cycle it was 97.5, third 94.8, and fifth was 95.2. So what we observed here basically, it means our given adsorbent MOF, that is IMOF 1A, is we are able to reuse it over different adsorption cycles. So it can be done in continuous as well as the batch flow. So we are going to put it in a batch flow process. So it is valid for the batch flow process. Then we went for the range of water systems. Since we have now modeled, we know what is the fundamental dynamics of its kinetics in a standard water samples and its reusability. Now we went for the real samples, like within we now use the uranium spike potable water, uranium spike lake water, then river water, because now river water is more contaminated, having the more cations, and then finally uranium spike artificial seawater, and then we will at the end we'll go to the seawater. In the end, we will mimic the seawater, and then we'll go to real seawater. So what we found that in use spike potable water dynamics is very high. So we are capturing almost 99.6% in 120 minutes. Similarly, use spike lake water, we are able to get the kinetics of 99.53% in 120 minutes, and use spike river water. So we are able to extract nearly 99.52% in 120 minutes. So for all three samples, the percentage is 99.5, nearly 99.5. Now you go use spike artificial seawater. Why artificial seawater? It has some 22 types of cation. It is a modeled, like whatever the seawater actually is there, we prepared the same seawater in the laboratory. Very standardized manner, that is given the formulation. And then we tested our kinetics. So we were able to extract nearly 27.81 ppb in 120. That is nearly 99.4%. Now you can see the remole percentage is dropped by 0.1%. 0.1% in terms of artificial seawater. Why it is? Because there are interfering cations. But still the drop is not very significant, and we are able to get 99.4%, which is significantly higher than 99%, and hence our adsorbent has the potential to do this in a commercial atmosphere or commercial setting. So what we did then finally what we have to do for the capture study, we have to go for the real seawater that we are going to do at the end. So what we did in the range of water system, we found that the capacity is what the maximum amount of adsorbent can be hold per unit area, per unit volume of the adsorbent. So adsorption capacity, as we go from the deionized water, artificial seawater, so till river water, like deionized drinking lake and river water, these are the non-sea water system. The capacity is higher, quite close to the 1600 or above 1500. But as we go to artificial seawater, capacity drops to the half. It becomes 625.6, and that is going to happen in all case of adsorbent. That is thoroughly natural. This drop should not be great. So this drop is commercially viable. So then what we did, the different concentration. Since we know the capacity is altering, so we did the relative concentration of stock and leftover. So we saw the with the different concentration also capacity is variable. And then we did the various interfering cations. Why interference cation? So in DI water there was only uranyl cation, that is uranium basically. But what are the interfering cation? In seawater, adsorb or take out any cation particularly, there is the biggest competition is from the potassium and sodium, because they are in the highest amount in the seawater. Then third concentration is the calcium. And there are few other cations in the sodium like strontium, magnesium, and titanium, and vanadium. They are the competitors of uranium. If you are going to if you use the uranium selective adsorbent and put it in the bulk water system, the sea water system, so along with uranium, titanium, strontium, vanadium are going to interfere in a very high amount, because they interfere the selectivity due to the similar molecular geometry or ionic size. whereas potassium and sodium dominates because they are in higher size, they are in higher number, higher amount in the seawater. So means like one uranium ion in the if you compare the unit volume of seawater, the one uranium ion has to 40,000 sodium ions. That is the ratio in the seawater of the other ions. And if the sodium is 40,000 times higher, you need to have adsorbent which is very selective and reusable. So while doing so, what we found the distribution coefficient for all other, since uranium will be the 100% in its standard model sample, and the lowest it was found to be in mixture of salt. When you put the mixture of all salt, the uranium capacity percent removal goes down to the 79%. Means that you cannot now extract the 100% of uranium. You can only extract the 79% of uranium, and 21% will be the other cations. So, but still it is a dominating. So we are achieving a good number here, and that's how the distribution constant is decided. So mixture of salt distribution constant is 261.27 because it is distribution constant of mixture to the distribution constant of uranium. So now let's compare the non-spiked seawater in various adsorbent in the literature. What we found, literature-based report is this one, IMAP IMZIP 90. It is the environmental energy science report of our own. Our MOP stands in the third in the literature. So now what we need to do, we need to go for the real-time dynamics. What is exactly happening in the pore? How the pore is handling the uranium that is within the MOP geometry. So we did that for Raman, TGA, N2, FSM, XPS, as well as the nano FTR. That will I will explain towards the end. So we see after uranium exchange, PXRD shift is not that great. Means crystal structure is not changing. It has a weak either or ligating interaction. During TGA, you can see the uranyl binding water loss is thin. Here, once the uranium is exchanged, we can see the water loss of TGA, which is because of uranyl cation has the extra water coordinated. And then we did the adsorption of uranium adsorb sample. So we saw there is a drop in the volume. This 430 ml is the or centimeter cube is the original MOF adsorption capacity for the N2. And when we did it for the uranium exchange, so drop should be there because this much of pore. Now the 288.79 ml per gram. So there is a gap of nearly 140 to 150 ml. Why this gap? Because this much of volume is now occupied by uranium within the core of the MOF. Similarly, we did the crack open. What we did? We cracked the crystal and did the FSM within the pore size of the dried crystal. And you can see the significant uranium present in this area and its percentage. And we further did the XPS survey, how the peak shift is occurring. So once we saw, as compared to the metal and uranyl nitrate to the uranium exchange MOF, we can see the uranium binding energy shifts to the lower. So what it does mean? It means that the uranium is getting stabilized within the MOF structure by some either van der Waals interaction or chemical interaction. That interaction we are going to characterize now. So similarly, we have seen the changes in nitrogen and the oxygen of the MOF itself. So because why nitrogen? Nitrogen is showing the significant shift. Hence, we got to know the nitrogen in the MOF is interacting with the uranium because both are showing the significant XPS shift. So going further, we also found the here the Raman spectra is very impactful here. You can see the uranyl nitrate has two humps here, two humps for the uranyl cation basically in the Raman absorption, and the uranyl nitrate above here that is single hump, and at the MOF I MOF 1A at the bottom red line. But when we go for the composite means the ion exchange phase where the uranium has been captured, then you can see composite of both uranyl phase as well as the MOF phase. So pick for the both. That is indicative of the successful exchange of uranium within the pore. And then the after this Raman, we further went for the how much is the shift basically. The shift is nearly of 20 centimeter inverse. Nearly 20 centimeter inverse. It means the bond order is either reduced or the bond is stabilized. So bond is weakened between the uranium and oxygen. And if the uranium oxygen bond is weakened, it means the uranium is ligating with the MOF nitrogen, and hence the overall the coordinative geometry is formed within the structure. So going further, that was the structural dynamics, how structure is interacting with the uranyl cation within the pore. Now going further, we need to find out its kinetics. So with so how the kinetics is driven? It is only chemical exchange, whether it is a molecular interaction or it is a thermodynamics. We all know that the free energy and thermodynamic equation that delta G is equal to T minus delta S. If the entropy goes up, free energy will go down, hence the adsorption will be beneficial. Why it is so? Because I want to explain this is more in a more significant way because this is the technique we use first time in the world for the adsorption experiment in the MOF domain, and it worked very successfully. And it is normally used in the nanomolar concentration for by peptide chemists, those who work in the chemical biology, and they will deal with the enzyme and their cofactor and their metal ion activators. There, this technique is used, and since we are going to use an ultra less amount uranium in our experiments, we also deployed this technique, which is called as isothermal titration calorimetry. This is used in the nanomolar concentration. It exactly uses thermodynamics, that is the enthalpy entropy change as well as the free energy change operating in the reaction. So what we did here, we give the doses of uranium in the MOF solution, and we identified this thermodynamics. So what is happening when MOF is treated with uranyl cation in a nanomolar concentration? You can see here the resultant data shows the delta G is decreasing. Delta G is the free energy. If the free energy is decreasing, it means reaction is a favorable. It means uranium going within the pore size is a favorable interaction. Whereas T delta S, that is entropy factor, is also increasing, but delta H is decreasing. Okay. So when I now the who is extremely competitive ion in the seawater with the uranium, like very facile competition is the calcium and sodium because they are in very high amount in seawater. Hence we chose these two candidates because they are going to interfere with the uranium. So then we did the kinetics and the kinetic as well as the rate study with the calcium using ITC, and it was found that delta G is negative, but T delta S also negative, and T delta is negative means the entropy is decreasing, and that is not the favorable change. And then we went for the sodium one. You can see the delta G, delta H, and T delta S. All three are negative. If the all three are negative, it means the adsorption is not occurring. Sodium is only going and coming out through the flask. It is not adsorbing. If it is adsorbing, then we have to look at the delta G first. So highest reduction in the delta G was in the case of uranium only. So now we need to understand this equation, why it is happening. As I have shown you in the first slide, there are DMA cations within the pore channels of the MOF. Once the uranium goes in, two DMA cation, uranium has a +2 charge, that is uranyl cation. Once it goes in the pore and you start stabilizing interaction with the Lewis basic nitrogen sites, the two DMA cations are now loose from that crystalline assembly, and hence it causes the increase in the entropy. You can see the increase in the entropy, and hence this reaction is a favorable. So largest decrease in the free energy, that is in the red band, and the increase in the entropy. If this is the ideal situation for the anion exchange within the particular assembly or within the particular network or framework, and that's why ITC help us why the uranium exchange is higher, because it helps us to understand the dynamics. And then what we did particularly after this, we went for the uranium capture in a nano FTIR. Nano FTIR is one of the best technique to understand in the 2D and 3D material 2D material dynamics in the vibrational spectroscopy. So how the functional groups are oriented, how their phases are analyzed, and in such a nano level, like 10 to 20 nanometer is just a layer by layer difference in the molecular arrangement. And if there is some atom is going and sitting within the layer, whether it actually exists there, the best way is to nano FTIR, because it will go the cantilever of nano FTIR. It is a laser guided measurement in a nano confined area where the cantilever will go only 10 nanometer down. It will touch within the molecule, then it will see whether that atom is here or whether that molecule is here or whether that bonding exists. So that was one of the brightest tool that we have. So this we did it at Oxford. So while doing so, what we observed, we did in a 200 nanometer size MOF crystal, and we did at several places. So we found that, so here you can see these two bands are concerned to the uranium and the MOF interaction, and hence we understood, and we have done the repetitive measurement. You can see spot 1, 2, 3, similarly spot 1, 2, 3, 4, 5, like all over the crystal and different crystal. So this was a bulk crystal which was extreme to the uranium, and then it was dispersed in the water, sonicated, made it to the finest size of 200 nanometer, and then we did all the nanospectroscopy, and we found that uranium, when compared to the uranium salt at the rate MOF, that is uranium adsorbed in the MOF, the absorption intensity for the uranyl cation goes nearly 20 centimeter inverse down, which is the reduction of bond order of uranium and oxygen. And since the uranium oxygen bond is weakening, means uranium and nitrogen bond within the MOF is strengthening, and thus the stabilization of uranium within the confined structure is forming. That is the one of the key tool to understand why this is happening. So after understanding this, we reaches to glance where we can see. So we reaches to a point where we can understand in this all water system what is exactly happening. So since we know the potable lake water, river water, and artificial water all are prone to the uranium adsorption, and the least prone is a real-time seawater. Okay, so then we have to do the ultra trace capture. Like, what is ultra trace capture? Because we know what we have done in a part per million concentrated solution to the part per billion concentrated solution. So, now we have to go to the real-time seawater concentration. What is the real-time seawater concentration? It is a 3.3 ppb. Means it is very less. It is called as the ultra trace concentration. It is named as the ultra trace. And now capturing this ultra trace is a good challenge, because that's what we wanted to have. And in that order, what we did, we had a 5 ppm solution first, then 1 ppm, then 500 ppb. Now we are going in parts per billion range, then 100 ppb, then 10 ppb. And then we did the uranium exchange for different concentration solution. We can see that higher the ppm, that higher the concentration of uranium, we are going to extract higher amount uranium from the MOF, because MOF has a high capacity. But now concentration goes very low, like 10 ppb. It is ultra fast concentration. Then recovering, finding this much of uranium in the solution, or the amount of time, and the volume available is very high, and time available, and the interaction sites is barely interact. So what we see, 83% of uranium is recovered, because interaction, probability of interaction in the higher concentration is always high as compared to the probability interaction of the lower concentration. So, then we did a real domain in seawater. So we were able to go down. So now we prepared the real, we analyzed the real seawater, which is 3.3 ppb. That is here. And then we did this extraction, and the leftover was the 0.93 parts per billion. What does that mean? Out of 3.3 ppb, only 0.93 parts per billion amount is left, and remaining amount is taken by the MOF in 300 minutes. Now we are not able to do it in 120 minutes. We are able to do it in a 300 minutes. That is 5 hours. And then we did a breakthrough. So this experiment really matters. What is the breakthrough? Breakthrough experiment is a real-time experiment done using the adsorption setup, in which we have a column and we have all the cations, competing cation, including strontium. You can see fed in the this column, and then we take the elution time, which cation is eluted first or which cation is retained last. So in the breakthrough, if uranium is retained, it will come as a last, because it is interacting with the column, that is a MOF bed, and it should be written by the MOF, and other cation under the force of or flux, it will come. So you can see the sodium comes first, then potassium, then calcium, then magnesium, then strontium, and then cadmium. But uranium comes last. It's because the uranium is held by the MOF assembly, and that's what the breakthrough is successful. This experiment is always essential for the commercial application. If any adsorbent fails this experiment, it cannot be commercialized. This is key point to note. Then we decide the enrichment index. Enrichment index is like how much uranium can be enriched within the MOF cavity as compared to the global competition. So for this work, in the MOF only, the enrichment index for nickel MOF, what we have made is highest, that is 5754, as compared to all the commercial, this SSPU fiber, POP AO, UI66, POP, DNU, POP, and MIS. They are the commercially available material. So we now are able to supersede this commercially available material, and hence now we can decide what is our rate of adsorption, whether it is globally competitive. So this is called as UES, uranium extraction standard, set by the International Atomic Extraction Agency, that is IAEU, which is at the USA, that decides if any adsorbent it is going to be used for the uranium extraction, it should extract definite amount of uranium in given time per gram. So what is US standard? US standard is 6 milligram. So in 1 month, if in 1 month, if of time, if any adsorbent is able to extract uranium of 6 milligram in 28 days, basically, then it is called as the valid for the commercial. This is the US standard. Our adsorbent, that is MOF, did that in 16 day only. We did not have the 28 day. In 16 day only, we are able to extract 6 milligram of US standards, and we finally in 30 day can extract 938 milligram. That is 150% of what US standard demands. Hence, this makes the potential candidate for the commercialization or commercial use of MOF. Then now we have to map globally all the commercial adsorbent present for the uranium extraction. So our MOF ranks here, that is capacity versus distribution coefficient graph. So what is capacity versus distribution coefficient? You should have the higher capacity, means the amount of uranium or amount of adsorbent you can hold. But you should have the higher distribution coefficient as well, means your distribution should be very fast. So adsorbent can have even lower capacity. But if the distribution is fast, you can reuse and extract the more amount of uranium. So in this case, our MOF has the second highest capacity in reported domain, and the with but significantly lower distribution coefficient. So means how this MOF can be deployed. So this MOF can be deployed for a longer time in the seawater to extract the uranium. That is its outcome. So how it is? What is the supremacy of given the given MOF system over the all other adsorbents? So now I will give you the competing material now existing in the market. So you can see PAF, the most like known material is the fibers. The why fibers? Because fibers are very stable in the seawater. Because seawater is a leaching material. It has a high amount of salinity and it leaches the metals and all. It leaches many ionic compounds, but does not affect the polymers like organic polymers. So fibers and carbons are the true competitions in that domain. And our MOF is ranked second in the global competition. We have published one more MOF by my one of colleague which ranks first particularly in this case. So this MOF now has the commercial potential for the commercialization, but there are certain problems by commercializing crystalline materials that we will discuss in the Q&A session. So going further, so we have done the thermodynamics, XPS and all. So by using the theoreticians, we try to understand what is the mechanics behind it, particularly what is exactly happening in the like we now know the what is which nitrogen is interacting with what. So we did a simulation for that, basically DFT and ESP structures. So what we found, what is happening basically, these Lewis basic nitrogens here are interacting with the which we are interacting with the DMA cation. Now they are finding weak interactions with the uranyl cation, and they are replacing 2 DMA, and these sites are occupied by the uranyl cation, and hence you can see this energy diagram where the homolymo distribution can be seen effectively. And here it is, you can see MOF homo is stable. Homo and LUMO is highly stabilized in case of uranium and nitrogen interaction in the given DFT optimized interaction site, and this is due to the exchangeable DMA cations and the Lewis basic side like called as the nitrogens. So overall, this is the picture basically, and with that, what we observe then. So since we know now all the data and the kinetics and all, we also like I would like to show you the video we have done in the real time seawater. This is in the real time seawater and DI water. And what is happening? You can see the uranium is changing the color here. You can see this happened in the fraction of few seconds. This is the overall 8 hours of time lapse we have collected in a confocal microscope with the control time frame. What it shows, these are the MOF crystals and the dilute uranium solution. They are not only changing the color, but the MOF crystal is not undergoing degradation because we are going to put in the real time seawater. If MOF crystal degrades, then we cannot reuse. So this video shows particularly how MOF stability doesn't affect, but uranium is being adsorbed. So far what we achieved in this case, particularly, what we achieved is the novelty. Like we have prepared an ionic assembly, that is IMOF one way, 1A, which is enriched with which has the Lewis basic sites in the form of pyrogenic nitrogen, which are derived from the linker. Second is the stability, reusability aspect, and third is the scalability. You can see the MOF has been scaled up to the grams. And the application spectrum. What is this application spectrum? Because it can work in the broad range of body. It is not only work from the modeled seawater or modeled water or lake water or potable water. It can be deployed in the real-time seawater. Then the kinetics and capacity. Kinetics is its capacity is high, kinetics is moderately fast, and the competence. How its competence is decided? Competence is decided by the enrichment index, and we have one of the highest enrichment index, that is 5754, as decided by the global standards, and high absorption capacity for the uranium spike water, that is 1336.8, as well as and 9.38 per milligram. And novel investigation strategies we deployed. We are the first to deploy the ITC and FTI and TFM. TFM data I didn't kept here. TFM, what is the TFM data basically? If some adsorbent goes and fits into the adsorbent goes and fits into the adsorbent, then the mechanical strength of that overall assembly increases, and that can be done by the TFM. That is a MOF mechanochemistry. It can be called as, and the strength can be uh, analyzed up to the megatons. Then what we are able to see the mechanical insight. What is there? The synergism, like thermodynamics, chemical interaction, and ionic transport. All three mechanisms are working together to do the selective and rapid separation as well as absorption of the uranium. And it opens the new avenue. What are the new avenues? That uranium capture and high risk pollutant. corroborated experimental rule. Remember, our history not only speaks about uranium capture, but it also speaks about how to characterize it, particularly by using nanonuclear, ITC, and TFM. Now, going further, I am going to conclude. Now, going further, what we have done extensive, like different than this. So that was one of the approach. And why this approach works? Because of the possibility of this interaction site, this Lewis acid nitrogen interacts with the uranium here. And so you can see the pore, how the pore geometry is. It is 6.2 angstrom to 2.1 angstrom. It is highly selective for the uranyl type of cation geometries. So pore is selective for the uranyl cations, and the ionic nature allows the ions to go out and uranium to sit in the pore surface. And this Lewis acid nitrogen forms the coordination geometry, which is particularly anchoring geometry for uranium. It does not anchor other components like sodium, calcium. So this actually morph geometry and its chemical or functionality within the pore decide the fate of uranium adsorption, and it makes it stand out adsorbent. So similarly, we have derived one more system that is called as a morph at the rate morph strategy. What it is basically. So in this strategy, what we have done, I'm just giving outline of this strategy. We know that the seawater is slightly alkaline, and we need to have a MOF stable at that, but highly competitive MOF. So what we did, in whatever we did in the previous study, we tried to enhance its adsorption capacity in a different approach. We form a first crystal of UI66 MOF. What is UI66 MOF? The MOF is made up of benzene dicarbonic acid and uranium and zirconium. Zirconium very stable SBUs, and we all know that zirconium is known for the stable compounds. We form this zirconium MOF, and then this zirconium MOF has the amino functionalized linker like this. This amino functionalized linker we functionalize with the imidazole to get an imine bond, and this imine then we form another MOF. So we have one crystal.
तुम्ही ती माहिती दिली डिपार्टमेंटल इन्फॉर्मेशन बघा.
and,
याचा
and
दुसरा
within this crystalline assembly, we form another crystal. So what we did, in one porous crystal we form another porous crystal. Okay, so now what we in this porous over this porous crystal we form another porous crystal, and now what we did, we want this particular geometry. You can see in the left hand side, to capture the uranium a particular type of geometry is required. That is this, the uranium, the OH, three water molecule, this oxygen, and this oxygen and nitrogen coordinating, anchoring to the uranyl cation that anchors the uranium. Okay, that is the particular geometry where the uranium can be adsorbed in the MOF. This is a part of MOF assembly. So we wanted to design that, but we were not able to design directly in a single crystal. So what we did, we identified two crystals by using this. Such geometry can be prepared. So hence we did UiO66 we first prepared by using this linker and zirconium, and this UiO66 we then functionalized by using this imidazole carboxylic imidazole uh, carbondiide, and then what we did, we treated zinc nitrate so that it will form the zip. This is another MOF. So we use one MOF which functionalize this ligand for another linker, then we form another linker, another MOF by using that linker. And now there is a crystal of UO inside this MOF. You can see here. And now we need to remove this crystal. After removing this crystal, only the geometry can be generated. So we made first acid stable MOF, which is base non-stable. UO is base non-stable but acid stable. We did acid-base chemistry. We functionalized it with some another linker. We form a zip, which is base stable but acid unstable. And now we use the base to remove the base unstable MOF. So UI was a base unstable. So we removed base unstable MOF in the alkaline solution. So only base stable MOF is left over. That is the IMOF ZIP 9050. This is the name of chemical name of MOF, and it has a porous structure. Why the selective porous structure? Because inside there were crystals. So from a crystal, we have removed the crystals selectively, and now we got this porous structure. This has been analyzed by the TEM. This is a TM image having a 200 nanometer of this uniform crystal actual image. And what this gives the geometry? This is the geometry present. You can see the zinc coordinated, and now this geometry is free. This nitrogen is free, and the zirconium from here is removed because zirconium removed due to the basicity or alkaline solution. Now this active site is free, and this active site is used for the coordination of the uranyl cation. That was the basic strategy, and that's why this paper landed up in the energy environmental science. That was the basic strategy. And then we did all the study like artificial seawater, river water, lake water, potable water, like all the modern water systems. It in my case, similarly, like 120 minutes of structure studies, and it absorbs nearly 99%, and it reaches the US standard only in 2 days. Like earlier MOF was doing US standard in 16 days, right? 30 days a standard limit. In 16 days earlier IMOF money was doing, but this, since it is a highly macroporous and it has a very particular interaction site or ligating site, it does this job in only 2 days. Only 2 days. And that is the best achievement. But we are facing problems commercializing this that I will discuss. So these 2 days, and the US standard was only 6 milligram, which we achieved in 2 days, and in using 125 days we are able to get the 28.2 milligram of uranium per gram of rock. So it is very high amount of uranium recovery from the seawater. And when we compare the commercial domain, this MOF has the highest uranium uptake right now in a commercial domain, like commercially available material or MOF material. Whereas the it's a theoretical this time and also time required is very less. You can see we are able to reach this 30 milligram in only few days, like nearly 25 days. Okay, and other adsorbent required very high amount. And that's why this material is highly demanding now. But the issue with this material is these are the crystalline nano. This is micro to nanocrystalline powder. And if it is a macro to nanocrystalline powder, what is the problem with such a powder is we to go back to as a surfactant beds, we need to make a composite polymer membrane or composite bead. Means some polymer will come in this polymer, this powder has to be encapsulated. And when we use as a composite, then capacity goes down. So we are still working over how this mask can be directly in some or other form can be utilized for the commercial application. That is its limitation. So with that, I think I have given the brief outline what we are doing in uranium extraction, and with that I would like to conclude my talk. I'm thankful to my group members at Oxford and ICER both. My both the mentors from Oxford, like Professor Jin Chong Tang, Professor Sujit Ghosh, and essentially European Research Council for funding this project, University of Oxford and ICER Pune. Thanks a lot for you being patient in the talk, and would be happy to answer the question.
Hello,
Hello.
I am audible?
Yes, you're audible, sir.
Yes, sir. Thank you, Dr. Yogeshwar Morris, sir, for delivering such an extraordinary and fabulous lecture to our audience. If there are any questions from the audience or participant, you can ask, please.
Yes, sir. Myself, Dr. Naire
Welcome, sir. Welcome.
from MSG College. Sir, your work is very good or very great, I think. But can we prepare this MOF at college level or some different MOF at college level?
Surely, you can prepare them at, like in the last map I had shown, now that you can prepare at a college level. The first map what
There
I
I
have
have.
seen,
Hmm.
first map
Yes,
what I
sir.
have shown, that also you can prepare at a college level. Only thing is, it's it is a two-step column procedure. That is a bit tricky, but still you can prepare it.
Or what applications can be explored with this MOF?
Already uranium and a selective critical mineral recovery is the first application, which is already explored. Other application will be the adsorption, like acetylene separation, because they are microporous and they have the Lewis-Basic interaction site. So you can do the hydrocarbon separation, CO2 adsorption, but this is also being studied now, because one Chinese group also published the acetylene separation with that. So these applications can be done. In case of second, the macroporous mop, you can do antibody pesticides related because they are the porous and having the functionalized side. So, and also photophysical study, that is luminescence studies you can do in
Yes.
second mop, that is
Yes,
zirconium
sir.
and zinc column mop. And nickel
I
is a
was trying.
yes, nickel
Yes,
is a
sir. Continue.
non-photophysical, so you can't do the photophysical activity with the nickel.
I was tried at the college that MIL 53,
Okay.
which is very well known, and I tried to compose it with the nano material,
Yes.
green synthesized, and then I want to use that composite for the photocatalytic or other nano applications.
Okay.
But there was some difficulties for calcination and all that after the
Yeah.
preparation.
Yeah. But there is also issue because once you prepare the nanomaterial within the MOF, what is the guarantee that nanomaterial is within the MOF? That you have to first characterize, because many times there is a either shape around the bottle or bottle around the shape. That is the thing. Many times it doesn't impregnate properly. Nanoparticle does not get into properly, or it is not stabilized in. So many times they are out of the MOF. They are not within the MOF. That
So
also
how do
happen. And
we analyze that?
for that, see, you have to choose the surface stabilizing atmosphere while synthesizing the MOF. And second thing is to analyze this, HRTM is the best way, whether it is within the MOF lattice. HRTM will tell
Thank
you
you.
whether it is placed in the
Yes,
MOF lattice. Yeah.
okay. Thank you. Thank you.
Any further questions from audience participant?
Thank you so much, sir, for your wonderful lecture. I have a question that what is the primary requirement of a material to decide whether it can use for a CO2 capturing purpose?
Very good, very good. So this question is actually well answered in the literature. What you need to have the like CO2 has a geometry, linear geometry, right? And it is a triatomic molecule. So it is basically its a net dipole moment is 0. So what you need to do, you need to have a molecule which has a functionalized size, which can allow the CO2 molecule can come in. That is it is a rod shaped molecule. So for that you need to have ultra microporous MOF. First geometry is ultra microporous MOF having the channel. Second, it should have the Lewis basic sides. What is the Lewis basic side? Like nitrogen and all those, which are the electron donor. Because such a Lewis basic side, what it will do? It will try to donate the lone electron pair to the delta plus. That is in CO2 the oxygen are delta minus, like partial negative charge holding, and carbon is a delta plus, that is partial positive charge. So that molecule can be bent and the overall symmetry can be disturbed, and the weak van der Waals interaction can be formed. That can be formed only when the something will break the symmetry of the molecule. Hence, you need to have a molecule or MOF or any crystal which is functionalized in the pore with the Lewis basic sides, and you need to have ultra microporous MOF. Just porosity is not enough. You need to have ultra microporous MOF, which has the pore size below nearly 22, I think, 0.2, like 22 angstrom or below. Basically, that will help.
Any further questions?
A wonderful lecture given by Yusuf. Thank you for the informative talks. Sir, I'm also working in the super porous materials like super absorbent polymer and the fly ash. So I have one hypothesis that can we use the cold fly ash as a metal organic framework, as it have the alumina and silicate layers, and we can modify it with the by combination it with the formic acids.
No,
Isn't it
actually,
possible for the CO2 capturing?
actually, see, CO2 capture you can do, but the fly ash, what you need to do, fly ash is basically raw material for the zeolite. Do you know that? A fly ash has the alumina and silicas, right? They are the raw material for the zeolites. If you do them a solvothermal treatment in presence of some modulator, you will get the zeolite, not the. No.
Any questions?
Any other questions? So
Dr.
on
More?
behalf of the organizing committee, I
1 minute,
express
sir.
my sincere gratitude to Dr. Yogeshwar More for sharing his outstanding research insights. I also thank to Dr. Prashant Kohli sir for chairing the session so effectively, all participants for their enthusiastic presence and interaction. Thank you, all of you.
Thanks a lot.
1 minute, sir. Sorry for interruption. Dr. More, sir, I have one question.
Yes.
Actually, you are extracting the uranium from seawater.
Yes.
So we know that the uranium is radioactive substance. So what preventive measures should be taken during this experiment?
Yeah, so very good question, very good question. So such a work can be done with the collaboration with the bark, because that you cannot do in the lab, radioactive. But the beauty of this work is that since we are doing the uranium extraction, there is uranium 235 and 238, right? One of them is non-radioactive, correct?
Yeah.
So nuclear property is different than the chemical property. So if you take the another isotope, your chemical property doesn't changes. What happens? Your chemical property doesn't changes. So what you need to do in the laboratory work, you need to take the non-radioactive isotope. It will give the exact same result, which as good as radioactive isotope. So you just need to take a non-radioactive element of it, do the laboratory experiment completely, and your final experiment you can collaborate with the bark or those who do the protected atmosphere. They can do the final experiment. So it is preferable to go with the non-radioactive uranium that is available in the market.
Okay, sir. Thank you.
Yes.
And at last, I would also like to uh, thankful to Dr. More sir for delivering such an extraordinary lecture, as well as to the organizers of this conference for giving me the opportunity to chair the session of such a wonderful person, Dr. Yogeshwar More. Thank you, one and all. Thank you very much.
Thanks a lot. Thanks a lot, sir. I'm concluding. Thank you. So can I leave now session?
Yes, sir.
आता आवाज आवाज नाही गेला आता चालू केलं तरी बोला पण आता बोला
फिटिंग आहे लाईव्ह हे बघा आता तुमचा
Next resource person will join shortly.
व्हॉट्सॲप त्याला प्रॅक्टिकल नंबर 6 बघा